Okay, so welcome back to our first talk of the morning, and it will be critical locus and solenoids for complex Henon maps by Tanya Firsova.
Good. Yeah. Can you hear me? Can you hear me better now? Okay, sounds good. So let me remind you what complex Henon maps are. Complex Henon maps are maps given by the simple formula. We have a polynomial p of x. We take p of x minus ay and x. This is, you can check that this is an automorphism of C2 just because you can calculate the inverse. The inverse is given by the formula that you see on the board. And this map, the real map version of this map was introduced by Henon as an approximation of the first return map of the Lorentz flow. And in fact, it's not just an example of polynomial automorphisms. All polynomial automorphisms in some sense are Henon maps. And precisely, Friedland and Milner showed that each polynomial automorphism with positive entropy is conjugate to a composition of Henon maps. So this is the example to study if you want to understand dynamics of the polynomial automorphism. And in this talk, I'm going to restrict to quadratic Henon maps. So my polynomial are going to be z squared plus c. And basically just for simplicity, because many results are easier to state and explain in this setting. So let us go to our favorite fractal. So this is the Mandelbrot set. And we know that for the points in the Mandelbrot set, parameters C such that the critical locus doesn't go, such that the critical point doesn't go to infinity. And let me remind you that for each polynomial z squared plus c, you can look at the Bircher coordinates that conjugates dynamics to z goes z to z squared. And we can look at the Green's function that measures escape rate as we go to infinity. And for the z squared plus c, we have dichotomy. Either the Julia set is connected, and in this case, escape locus, the complement of the filled-in Julia set is a disk. And this happens when the parameter belongs to the interior of the, just to the Mandelbrot set, and when the parameter is outside, then the Julia set is a Cantor set. And escape locus has topology, right? So it's complement to the Cantor set. So I want to state some known results similar to that for Henon maps and some questions. So let me remind you the dynamical filtration for Henon maps. So we look at the sets, we take R big enough. So if some R works, any bigger R works. And for every Henon map, there is an R that works, that provides the dynamical filtration. So we look at the set B plus, that is on the right. This is B plus. Here, absolute value of X is greater than the absolute value of Y. And sometimes we allow equality, and absolute value of X is greater than R. X is big, and X is bigger than Y. And V minus at the top is absolute value Y is bigger than I, and Y is bigger than X in absolute value. And what we want from this dynamical filtration, and what we want from this dynamical filtration is what is shown on the picture. We want if we take an orbit in V plus, we want it to stay in V plus and go to infinity. And if we take a point in V minus, we wanted to stay in V minus under inverse of the Henon map. Sorry. We wanted to stay in V minus under inverse of Henon map because Henon map is invertible. So you can look at forward iterates and backward iterates. And then there is an interesting box and lots of interesting things happen there. So the points, they can enter like under forward iterates from V minus, they enter, and some of them stay there, and some go and escape to V plus. And we introduced the escape sets, so you should think about the complement to filled-in Julia set for polynomial. And again, in this case, there are two of them. There is forward and backward. And since we chose our dynamical filtration, U plus is inverse imagers of V plus, and U minus is forward imagers of V minus. Okay, so now we look at the, in this case, we have several Julia sets and several filled-in Julia sets. So we look at K plus, which is complement to the forward escape blockers. And this boundary is J plus. The same for J minus, and then we look at the intersection of K plus and K minus, J minus and J plus. And the sets J plus, J minus, and J are all called Julia sets. Like the most standard is to call J Julia set, but all of them can be considered Julia sets. So J plus, J is compact, J plus and J minus, sorry, I should put it. J is compact, J plus and J minus are not. Now we have, we want to go back to the virtual coordinate and Green functions. And again, and we, the structure of U plus and U minus is well understood. I'm going to remind the known results. And phi plus is a function that conjugates dynamics to Z goes to Z squared. In this case, it doesn't conjugate, it semi-conjugates. It's a function from C2 to C. And let me draw the picture, that, and it will be important for me. So this is my dynamical filtration. And I'm looking at the level sets of P plus. So P plus is a function from C2 to C, so I can look at the level sets. And first, let me, this function is, this function is well defined in P plus. Like the same as for one dimension, you shouldn't expect it to, like maybe it extends, maybe it doesn't, but a priori it is at infinity. And in this case, infinity is V plus. So we look at the level sets, and this level sets, like I've drawn it like this, but they are almost vertical. So at infinity, they're almost vertical. You can think about phi plus as x. And you can look at phi minus, and you can think about phi minus as y. And we can also, we can now ask questions, is phi plus defined everywhere? And in this case, the answer is always no. It never defined everywhere. It can, you can take the foliation and propagate it by dynamics. So you get a foliation everywhere, but phi plus itself is not defined everywhere. You can define powers of phi plus. It's always the case that it doesn't extend to all of U plus. And the same, like you can do the same for U minus. There is some small subtlety that you cannot conjugate inverse dynamics to Z goes to Z squared. It's going to be Z squared over A. We can define the Green's function measuring escape rate of escape to infinity, and again, two Green's functions. And Green's function is log of v plus. So you think about it as log of absolute value of x in v plus. It is defined everywhere, the same as for polynomial maps. And it's a pluri-subharmonic function. And it's pluri-harmonic in U plus. And if we look at those leaves, like if we take these leaves, we can propagate them by dynamics. And each leaf is C. And each leaf, like it stays in, when you propagate it by dynamics, you don't change G plus. So it stays in the same level set G plus equals constant. And it's dense there. Okay. So let me introduce or remind you about solenoids. So I'm gonna need both geometric description and algebraic description. So let me start from algebraic description. I take the unit circle, and I have a map z goes to z squared on the unit circle. I can take a point, and I can take sequence of points such that each previous point is I take a point z naught, I take one of its preimagers. And again, one of its preimagers, and so on. So I have the set sigma such that I have each point belongs to the unit circle, and if I square zi plus 1, I get zi. So this set is has a structure of the group, and this is a solenoid, and you can do that for any, like, there is nothing special about z squared. You can do it for z to the power d, but we'll restrict to the power 2 in this talk. Now I want to understand this set geometrically, and what we're going to do, let us take a torus, filled in torus. And let's take this torus, stretch it, and wrap it around twice. And here there is subtlety for general degree D. It shouldn't be naught. For T, it can't be naught. So for T, you just wrap it around twice. Then do the same thing. Take this long torus, stretch it even more, wrap it around inside it twice. And keep going like this. And see what you get at the end. Right, so what you're going to get at the end, you're going to get, like locally, you're going to get a segment times a Cantor set. So it is a segment times a Cantor set, and there is monodromy. So this monodromy, you can think of Cantor set as sequence of zeros and ones. Infinite in one direction. And you take, you add one to this sequence the following way. Like, let's say the first element is 1, you have 1 plus 1. So the 1 goes to the next place. This is called the add-in machine. If it was like 1 plus 0, you just get 1. But if you get 0, you move 1 to the next place. And you keep going. So for example, from sequence 1, 1, 1, when you add this 1, you get a sequence 0, 0, 0. So this is a monodromy on the solenoid. So you can think, if you want to think about solenoid geometrically, just segment times the Cantor set and specific monodromy. So solenoids appear like at every place for complex Henon maps. So let's see an example of the theorem by Hubbard and Oberstworth. Hubbard and Oberstworth gave description of the set U plus, and they gave like several descriptions. So I'm going to state one of them. So take this set V plus, like look at this set. You look at this set and you realize that this is a filled in torus, right? So this is like the filled disk, and you go around, and this is another circle in the torus, non-filled one, and you have this extra dimension, right? So it's instead of being three-dimensional, it's four-dimensional. Now let's see how Henon map acts on this V plus. We can take. Do you see if I write here, draw here? So we can take, like, let's take V plus and map it into, we know V plus goes to V plus. It goes the following way. You take a disk and you get two disks. So, and these disks move as you go around. So that's exactly a solenoidal map. So the map from V plus to V plus is solenoidal map. Now, U plus is inductive limit of V plus. So we shouldn't be looking at like the map from V plus to V plus. We should be looking in the other direction, right? Which we're taking pre-imagers. But when we have, still, let's look at V plus to V plus. So we have the solenoidal map, and the fundamental group is just Z. And this solenoidal map maps Z to 2Z. Now, if you're familiar with the inductive limits, you can see that you can lift it all to the inductive limit. And you see that, so you have a sequence like Z, and it's, I should be drawing it in this direction. It's infinite, and every time you multiply by 2. So what you get is the fundamental group is dyadic group. Dyadic group meaning that you look at the elements with denominators powers of 2, with integer divided by the power of 2. So this is a fundamental group of U plus. And in general, this is the description of U plus. So the description follows from inductive limit. We have a torus that's mapped inside of the torus, and we take the inductive limit. So when we do that, you can think of S3 as two tori glued together. And you have a torus, and you have this extra torus. And you fill, by pre-images, you fill in this extra torus, but you don't fill it completely. You're missing a solenoid. So this is the topology of U plus. And I'm keeping completely this extra dimension because it's a fibration over this extra dimension. Okay, so nothing is different for U minus. Now, the question I want to address is, what about the intersection? So in one of the, I'm not sure which one, like in Bedford-Smiley series, it says nothing is known about the intersection. So let me now state a couple of theorems that are known. This is a question that was posed to us by Eric Bedford. Is it always connected? And I think, and we proved that it's connected. It probably was known before. So I won't claim it as our theorem, but we couldn't find it in the literature. So let me explain you the proof why it's always connected. So assume that there is like util. First, let's look at one component, like standard component of U plus intersected with U minus. We're going to prove it's 1, but let's take the filtration and let's see where this standard component is. So let's look at the component. Let's look at the diagonal. The elements on the diagonal, they belong to both. They belong to U plus and they belong to U minus. And elements like close to it also belong to both. So this is our standard component. Assume that, so this is U standard, and assume there is another one somewhere. And there is this component, it's also foliated by the leaves of foliation defined by phi plus and which I'll call stable foliation. And it's foliated by leaves of by unstable foliation. Let me, I have this component, and let me take its high iterate. And it's going to be like high enough so that if I take a leaf of the stable foliation intersecting this component, this leaf will be in the will also intersect the region where I have a nice description, where I know that it's almost vertical. So this is L that intersects U tilde, in fact, some height component, and this is the same L. Now I want to arrive at the contradiction, why this is not possible. So I have this leaf, I know it intersects my U tilde. Maybe it can behave like in this U tilde, like it can go like wild there. It can intersect the boundary many times, but it has to intersect the boundary because I assume that it's a special component and it intersects my component, my standard component. And not C, US for standard. So it means that it has to intersect the boundary. Let us look at the function G minus on the boundary. G minus on the L on at the point Z such that Z belongs to L intersected with the boundary of U tilde. It has to be equal to 0 at every point on the boundary. So it will be like more or less the only proof. So please, in this talk that I will completely present, so please ask questions. I hope everyone will understand this proof. So on the boundary, either G minus is equal to 0 or G plus is equal to 0. It can't be G plus because this is a leaf of the stable foliation. So it's G minus. Now, if it's bounded, so this is a leaf L, if I have a bounded region, where on the bounded in L, where on the boundary G minus is equal to 0. And then it's equal to 0 inside, and it doesn't belong to U plus. So this region is not bounded on the leaf, which is possible because it's like it can have as many foldings, infinitely many foldings there. So far, no contradiction. So I have unbounded G minus equal to 0 on the leaf. And now I want to write the contradiction by looking at the leaf here. So I'm looking at the leaf L, and I know it intersects, and it intersects countably many times, right? It's dense in G minus equals to R, like it's it intersects here finitely many times and then intersect there even more times. But let's look here. So we'll look at this leaf L. And we want to show that it's not possible that there is unbounded G minus equals to 0 there. So let us look at the So when we look at the intersection of the leaf, like real picture is misleading. The boundary is here. This is not the boundary. Right? The boundary is the diagonal when x is equal to y. On the boundary, G minus is approximately equal to G plus. So it means that G minus is approximately equal to, G plus is equal to log R. So it's never equal to 0 on the boundary. So this tells us that every G minus equal to 0 is bounded on the leaf. So let me just draw it. This is G minus equals to R. And we have, like when we have this leaf, we have countably many. This level sets G minus equals to R, and G minus equals to 0 has to live inside. Or I can just say that the intersection does not cross the boundary. So it has to be bounded. Questions? Okay, so I hope I convinced you. So it's always connected. Now I want to give, I'm not going to give a complete description. I'm going to give some result about the intersection. So I want to look at a Henon map that is a horseshoe map. And the horseshoe map means the dynamics is conjugate to two shift on by infinite dyadic sequences. So if you want an example, take C outside of the Mandelbrot set and look at x squared plus C, x squared plus C minus AY x. C doesn't belong to Mandelbrot set, and A is tiny. So take a map outside of the Mandelbrot set and perturb it a little bit. So you can think, when A is small, you can think about Henon map as a perturbation of quadratic polynomial, like acting on parabola. So that's an example of a horseshoe map. The set of horseshoe map is big. We show together with Remus and Reluca, we show that in this case, the homology of U plus intersected with U minus is a direct sum of dyadic groups. So we would very much like to describe pi1 to understand not just the homology, but fundamental group. And in general, we would like to know whether, to have this description in general and to know that does it reflect the properties of the Julia set. We know that U plus itself doesn't reflect the properties. We know that if for polynomial, escape locus reflect the properties of the Julia set. For Henon map, U plus and U minus does, maybe U plus intersected with U minus does. So I promised it's going to be the only proof in this talk. but I have another one. So let me just say a few words here. So the reason we can describe it is because U plus for all Henon maps, U plus for all horseshoe Henon maps, U plus intersected with U minus are the same, because there is a conjugacy. This conjugacy was constructed by Barges and Vermeer using holomorphic motions. It's not, they didn't provide like a natural holomorphic motion, but they provided some. They constructed a holomorphic motion that provides this conjugacy. So it means that we can take any Henon map and prove this theorem for that particular Henon map, and it will of any horseshoe Henon map, and it will hold for all Henon maps. And there are particularly easy ones for this problem when you take a quadratic polynomial with the Cantor set on the real line. And then using Meyer-View-Torres, you write Meyer-View-Torres sequence, and you can, this is Meyer-View-Torres sequence. And we have zeros here. So it tells us that these two are equal. And the nice thing about like the start of this proof is you can do the same for pi1. Like meaning if you can find a particularly easy horseshoe Henon map to describe pi1, then you have a description for all of them. The question is, which one is particularly easy for pi1? Okay. Okay, so let me talk now about my second main actor for this talk. I want to talk about the critical lockers. So we know that for polynomial maps or like rational maps, critical points are very important. For polynomial automorphisms, like we know polynomial automorphisms are invertible, so no critical points. But it's still tempting to, like, they're very important, so there should be some analog. And the way, and Bedford, Smiley, and Hubbard did define an analog. They used the following fact that if you look at the, let's look at the polynomial, let's look at the critical point, and let's look at the green function. If you look at the critical point of the polynomial, it's also a critical point of the Green's function. So there are Green's functions. What about the critical points for the Green's functions? These Green's functions are mapped like plurisubharmonic functions. So critical points, like you have to be careful how you define them. But if you restrict the Green's function to foliation, like for example, if I take my foliation of my stable foliation f plus, which is almost x at infinity, then I can look at the Green function g minus, and I can look at the critical points. There are laminations of laminations in quotes for G plus and G minus. They are like, there are Riemann surfaces inside of G plus and G minus stable manifolds. So we can look, like we can take G plus and restrict G minus here as well. And we can look at the critical points. And we can do the same for G minus. So this is how the critical locus was defined by Bedford and Smiley. So first I give the definition in the escape locus U plus intersected with U minus. I said critical points of the Green's function. You can also like look at phi plus and phi minus. So critical points of the Green functions are exactly tangencies between the foliations. Phi plus doesn't extend to all of U plus, but if you look at d log of phi plus, it does extend because powers do extend. So d log of p plus is a well-defined one form. D log of p minus is a well-defined one form. So you can look at the zeros of this one form. And you get an analytic set. And this analytic set is the critical locus. And Bedford and Smiley showed that this critical locus is always non-empty, and closed analytic subvariety of U plus intersected with U minus. And like this is J plus, and let me, like I also have J minus, and there I have the Green's function G plus. So this is another two critical loci, CU and CS, that were defined by Bedford and Smiley. And notice that J plus and J minus are not always laminar. So you look at the stable manifolds inside of G plus and G minus, look at the critical points there. And these critical loci can be empty. And again, they remark that the relation between like these three critical loci is quite mysterious. And okay. So let me show how Bedford and Smiley, let me state how Bedford and Smiley like use the critical locus to show that this is a useful notion, that it, like we define the critical locus, we want it to be an analog of the critical points. Like in which sense is it an analog? So what Bedford and Smiley showed that if we look at this unstable critical locus, then it's empty if and only if J is connected. And in fact, they have a list of equivalent conditions. So I'm stating here 4 conditions, and there will be more, and they have even more in their paper. So this is Bedford, Smiley, I believe 6. So we look at the unstable manifold of the saddle point P, and we intersect it with K plus. So J is, so you want to know whether the whole Julius set is connected. You can understand it just on one unstable manifold. If you see that it's connected on one stable manifold, it's connected. And it will be connected on all of them. And the picture on the right is disconnected case. So this is for, they called it unstable connectivity. And I should have said this is for dissipative Henon map. So Jacobian is less than 1. You can do the same for Jacobian is greater than 1, but then you switch stable and unstable. So the picture on the right is the opposite case. There is, and like this red star is the critical point. And it's not the only critical point, it's just the one that I emphasized. There are many more. Unfortunately, there is no Raluca in the audience. So she would, yeah, we can send her a message. She would be able to answer the questions. And I should credit her for all the beautiful pictures. There are some pictures produced by me in this talk, but all the beautiful pictures are produced by Raluca. Again, like we're going to send a message to Raluca, and she should be able to answer all the questions. Okay, so now let's go back. Let's try to connect the things with what we talked before. We talked about the solenoid and its inverse limit of the z squared on the unit circle. You can look at the complex solenoid, which is the inverse limit on C star. So all C with the 0 removed. And again, it has a group structure. And topologically is the same solenoid times just has an extra direction. But if you look at the group structure, it has complex structure. So this is complex solenoid. I'm going to take the complex solenoid, like half of this complex solenoid. I'm going to take the points that are greater than 1 in absolute value. Okay, so let me first state 2 more conditions that Bedford and Smiley list. So let me go back to the previous slide. So these are conditions of unstable connectivity. They can also be unstable connectivity can also be described in terms of G minus plus, and I think I missed the definition. So G minus plus is G minus without J. So I remove J from G minus. And if it's unstably connected, that this G minus plus has a Riemann surface lamination by simply connected leaves. And the function phi plus, it doesn't extend to all of, like, remember phi plus, like it's defined here, it's almost x. Its powers extend, but it itself doesn't extend. But it extends to this G minus plus if the map is unstably connected. And moreover, if it extends, then the map is unstably connected. So you should think that we have here J minus, and if the Julie set is connected, you can push this phi plus all the way to J. And this, so this is G minus, and if it's like, we see these intersections with phi plus, so it extends there, we can say, what is the value of phi plus at every point? This function phi plus defines a conjugacy to the complex solenoid, right? Because we can see what is the value. So we can think, we can see what is the value, and this z goes to z squared relation is preserved, also preserved. So they show, Bedford and Smiley shows that there is always a semi-conjugacy from J minus plus to complex to this half of the complex solenoid. And I want to visualize this complex solenoid in some cases for the Henon maps using critical lockers. So first, let me, like I defined the critical lockers, let me give some things that we know about the critical lockers. So first, the critical lockers, there are a lot of places where the foliations are tangent. So it means there is no critical lockers. So what the lemma says is that I can take a strip of a certain size, and this size is determined by the Jacobian. I can take this strip and its images and pre-images. And outside, there is no critical lockers. Very simple, like, calculation. Now, if I look at this, so this is my dynamical filtration. If I look at this strip at infinity, so here x is equal to infinity. We know how phi plus looks like. We can calculate how stable foliation is just x. We can calculate unstable foliation. Unstable foliation at infinity is parabolas. So when we look at infinity, so we have, like, this is x equals to infinity. So we have one foliation that you can think is vertical and another foliation that is parabolars. So it means that we have critical locus there. And you can do this calculation, so you can show that this critical locus is asymptotic to the x-axis. And again, for quadratic Henon maps, because 0 is the critical point of x squared plus c. And this was basically, this was done by Lubitsch and Robertson. They looked at the perturbations, but they calculate, like we just checked that their calculation works in general. So it means we have this prime end of the critical locus. And this is another proof that critical locus is always non-empty. So we have this prime end, and how I'm doing on time? 5 more minutes, okay. So let me then mostly show pictures. So this is a picture of the critical locus in the real plane. It was produced by the program tangences, and recovered by Remus on a very old Mac. And it was produced by Papa Dantanakis in Cornell. So the critical locus is where the green turns to red. So this is the primary component. And then you can see, like, it's for sorry, I'm going in the wrong direction. So this is its first pre-image. So basically the y-axis. And then you can see its image. These are the imagers, and over there are pre-imagers. So here you can see them going all the way to J. An easy calculation show that there is this primary component in infinity, and in general, it's not true that it goes all the way to J. It's true in certain cases. And let me take the leaf of L plus and show the critical locus on this leaf. So we have G plus equals R, another G plus equals R, where R is big. So the critical locus is a figure 8. This is the prime. This is pre-image of the primary component. Then we have this is the primary component, and it keeps going like this. And if it extends all the way to J, it keeps going like, it always keeps, our description tells us that it always keeps going like this to infinity, but it doesn't tell that it keeps going like this to all the way to G equals 0. If it extends all the way to J, it keeps going like this all the way to 0. And the solenoid that we would like to see are the points G equals 0 here. So the solenoid is G equals 0 is the Cantor set. So E, we have the description of the critical locus all the way to G. We see the solenoid on each intersection with the leaf. So we see the Cantor set, and we know that we can multiply this we have a holomorphic motion of this Cantor set. So this is G times a disk. And this I'll skip. So this is Hubbard's conjecture that the critical locus goes all the way to G. And we prove that if it does, then it's a complex solenoid. I think I'll stop here.